Hello, my name is Lao Zue and my number matrix is J20A0463 and I am student of FIT3123. I would like to present about the production of Spirulina Platensis using Photobioreactor from microalgae. For introduction, microalgae are microscopic organisms with color pigments that live in aquatic environments. Spirulina is a photosynthesis filamentous blue-greens microalgae that grow quickly. Since microalgae have a tight integration with their environment, the facts that are direct connect to their environment must be at optimum value like temperature, light, nutrients, and pH. Photobioreactor refers to a closed system in which to optimum environment for growth is attended by managing the system. The aquaculture and agribusiness farms photobioreactor are also integrated with wastewater treatment. The objective of mini project is to increase the productivity of the microalgae in photobioreactor to produce various nutrition modalities of spirulina on a small scale productions.
For the next part is method and discussion. First of all, we go through the photobioreactor design and equipment. First, the open type PBR consisted of a vertical matte polymetal halide tube with a 24.5 diameters, 8 m of height, 3 mm of thickness, and a total volume of 84 liters fixed at the center of parallelepiped shape cage formed by metal panels and positioned on a stainless steel platform with 4 legs equipped with wheels to allow movement of the PBR. Then, 4 light blocks were placed on each vertical panel on the cage at the mid-height of the plastic tube. Next, a waste collection system was installed at the bottom of the tube under the platform to allow the draining of the tube content at the end of each cultivation cycles. Then, the aeration system was made of an air bubbling device. Then, FB provided by an aquarium pump placed on the upper cover to deliver airflow of 400 L per H controlled by an airflow meter. Last, an aquarium-type temperature control heater immersed at mid-height in the PBR tube. That's all.
Second, light measurement. An illumination meter measured lux around the PBR tube. The sensor was placed on the PBR tube at the mid-height facing each light blocks to measure the illumination level. Each light block location were illuminated when all 4 blocks were on. Since daylight fluorescence tubes produce the light, photosynthetic photon flux density (PPFD) units could be used to indicate the illumination level. 3. Preparation of the microalgae culture media. To maintain consistent condition for comparison microalgae production cycle runs, the water utilized was the constant quality since it was freshly pre-filtered 0.2 m tap water. The zero culture medium composition was employed for inoculum growth and the PBR production cycle for each microalgae. 4. Culture medium for PBR spirulina production. All nutrient solutions were introduced to 50 liters of water in the PBR tube. Air bubbling at 40 liters per hour commenced before microalgae production to mix the medium. Water filled in the PBR to 80 liters. The culture solution was homogenized until the submerged aquarium type heater increased the temperature to spirulina optimal growth temperature.
To reduce stress on the microalgae culture, just 2 opposite light blocks were switched on for 24 hours after cycle began. The air bubble rate for 2 weeks of the spirulina production cycle was 200 liters per hour. To avoid culture media forming, the flow rate was decreased to 100 liters per hour. By reducing air bubble, spirulina filament breakage was kept to a minimum. Every 2 days, an equivalent quantity of growing medium must be provided to replace the evaporated water. Depending on the air bubble velocity during production, culture medium was provided between 0.3 to 0.7 liters per day. The culture medium containing the biomass produced after each production cycle were drained through the waste pipe located underneath the bottom platform and connected to the PBR tube. The tube was thoroughly washed with tap water. 3 liters of an oxidant alkaline solution of sodium hydroxide and sodium hypochlorite was gently sprayed from the PBR's open top to remove organic particles from the inside of the tube. To balance the pH of the wastewater, drain the alkaline solution and rinse the tube with only a little tap water. The tube was emptied after being rinsed with filtered tap water.
In conclusion, a small-scale photobioreactor created in a conjunction with the specific production method may make it easier to cultivate Spirulina platensis to provide a reproducible culture media for microalgae in the growth stage with consistent quality. On laboratory scales, the repeatable culture media created may be used as standard and flash material for further scientific investigations, such as small-scale harvesting method required for microalgae strains with smaller size than spirulina filaments. Small production may also use the photobioreactor productions to safety grow and harvesting microalgae biomass for nutrition supply. That's all we want to present, and thank you.